Okay. Good afternoon, everyone. Thanks for joining. Today, our speaker is Shamanti Datta from Institute of Mathematical Sciences, Chennai. She'll going to talk about bulk gauge field from boundary safety using ERG. Over to you, Shamanti.
Okay. Good afternoon, everyone. Uh, so, as you have seen, title of my talk is bulk gauge field from boundary safety using ERG. This is a work done with Bala Satyapalan and Pavan Dharani Pragada from IMSC Chennai. So, first I will start with a motivation of my talk. There is emergence. Main motivation is emergence of extra dimension in quantum gravity. And most explored example of it can be given from ADS-CFT, where the scale of the boundary can be interpreted as radial direction in bulk. So one crude way to see that is consider radius space in Poincare patch, where uh, it is scaled by a factor of 1 by z square. So whenever you are in fixed z looks like lattice spacing of the boundary theory. So one can speculate that change in z should give a scale change in boundary theory. Okay. Now there are many with respect to this statement, there are many work regarding this uh, scale and radial duality. One is that whenever we write ADS-CFT conjecture, this both side of the QFT and gravity side, both side needs renormalization. Where QFT side have UV divergence and gravity side have IR divergence. So one scheme of finding correlation function, one scheme is finding correlation function or beta function of QFT using renormalized gravity action, where we cure the IR divergences. So this work is done by Henningston, Skendries, Haro, Solodukin, Skendries, then Bianchi, Friedman, Skendries in 2001, 2 and 2000 years. And actually a clearer picture of how to relate Wilsonian picture of bulk and boundary came in the year of 2011 by in Liu, Rangamani and Faulkner paper. So where they are telling that is bulk action you can write in two parts. One part is totally bulk part, another is a boundary part. So where epsilon is a point which is very nearby to the boundary. And in boundary, there is a effective action, Wilson action. So I will come to later. Effective action means a low energy effective action. We will talk about it later. And they are showing that this totally bulk part SP is interpreted as I effective. Like they are showing delta SP, how it is changing with epsilon. That gives Hamiltonian of radial evolution. So from ADS-CFT correspondence, one can tell that this should be related to the RG of the boundary, because epsilon is like variable of z, so it is related to scale, and SB is they are interpreting as I effective. So this is one important interpretation of Wilsonian picture in both sides.
Just to clarify, I mean, I guess you're not in purely ADS space, right? I mean, because you're talking about RG and all that. I mean, if you're just purely in ADS space,
Yeah, we
it's a
will part up
conformal
actually.
theory.
Yeah.
This is not a conformal field theory because you're talking about beta functions
No, we
and
will part
flow
up
and
around. Sorry. Yeah, we are not at conformal field theory. So conformal field theory is in the boundary only, but we will perturb. So then it is not pure ATS. So then it will give the ATS the radial evolution.
yeah, even in the CFT, you're not in the pure CFT. I mean, it is flowing or something. I mean,
But if you in fixed point, it is not flowing, right? Like
so you're
RG flow
talking
is
about
not.
RG flow and everything, right? I mean, so you have some, just to clarify, I mean, in the radial direction, you have some, some dilaton or something, which may ensures that the beta function is changing, and then there is a point. Is that the picture
Yeah,
you have?
yeah.
Okay.
Yeah. Okay.
Okay.
So okay. So to clarify it better. I have taken.
Yeah, sorry to interrupt, but just to understand the point that Justin was making. So you're looking at spaces that are only asymptotically ADS, is that right? And
Yes.
then in the bulk, they may, in the bulk, they will in general differ from the strict ADS5 or
Yeah.
whichever.
Yeah.
Okay, so okay, that's what I guess that was Justin's point also.
Yeah.
Yeah.
Okay,
Yeah.
okay, thanks. Yeah, thanks.
Okay, so to clarify this thing better, I have taken a picture from the paper of Faulkner. That is like there are two pictures. One is at boundary and bulk. So boundary, what we are doing is this lambda naught is UV cutoff, and we are getting a low energy theory at lambda. So we are integrating out modes from lambda naught to lambda, and we are getting a Wilson action of in a scale lambda, and this lambda star is an intermediate scale. So the dual picture in the bulk is you have taken you have cut off your boundary at z is equal to epsilon naught, and you are integrating out all the z, all the z up to epsilon, and there is here is also intermediate scale epsilon dash. So that is the dual picture. Whatever is boundary boundary Wilson action is given. So okay. So from this one question arises that here everything whatever statement you are giving is giving in terms of bulk. Like we are telling bulk part or sorry boundary part of the bulk action, how it is changing with epsilon. Now the question is, can one make another uh, holographic RG equation, which we can start from boundary RG equation, but we will not use ADS-CFT conjecture. But we'll find ADS action from that holographic RG equation. So if someone can do that, so that will give further insight into correspondence between bulk gravity and boundary CFT. And we choose exact renormalization group for this purpose because concept of scale is natural in this scheme. So to this point, I will tell a little bit about what is ERG. What is ERG is instead of whenever in old days removing infinities from the correlators can be replaced as a is to be seen as a process of changing scale, where instead of taking UV cutoff to the infinity, we put two finite cutoff in the theory like lambda naught and lambda, where theory is flowing from lambda naught to lambda. And whenever you are changing scale from suppose lambda naught to lambda, or here I have written lambda 1 to lambda 2, you will produce some non-trivial actions. So non-trivial actions will also have irrelevant terms in the effective low energy action, which will be suppressed by the mode lambda by lambda naught, or here it is lambda 2 by lambda 1. So whenever you take continuum limit, those non-renormalizable or irrelevant terms will get suppressed. So in what happens is this suppressing is done. How these high energy modes are suppressed? It is done with a analytic cutoff function. But a result of that is the new correlator. The correlator at the low energy can always give back the old or bare correlator. So that's why this name exact comes. So there is no loss of information. Okay. Now, whatever I told qualitative statement, I will tell mathematically in this slide. That is, suppose we are choosing a bare action. Okay, suppose we are choosing a bare action where you can see this. We have chosen a cutoff function like kp by lambda, where as we have taken this, you can see that this is a theory at scale lambda naught. So the property of K is such that it tends to 1 for x tends to 1 and 0 for x tends to infinity. And after that, what we do is we decompose phi into phi l plus phi h, and also lambda into delta means this propagator into a low energy part and high energy part. So this phi l and phi h means you can see from here that it carries out only low energy part, which is momenta, which is lower than lambda, is carried out by this propagator, and the other are by this propagator. And what we do is we integrate out phi h, and z is written in this way. We can write it as a function integral over phi l, where this s lambda phi l is given by this. Now you can see that this new theory is at a scale lambda, and this I lambda is the non-trivial part, where I was telling that non-renormalizable parts come up. Okay. Now one can find, after one can find this is called Wilson action. After one can find S lambda I, then one can find how this S lambda changes with scale lambda. So that is given by Polchinski's equation. So this equation is given by this expression. So I want to point out some distinct features of this equation. One is the main structure of the equation is given by this part. Okay. You can see this you can understand this represent a non-PI part of. If you see in terms of diagram, which I'll tell in the next slide, it is a non always part contains both PI and non-PI. So this part, if you take is only interactive part, this part goes, so that is not important. And this part comes where note you may not want to note that eta by 2 is the anomalous dimension of phi, and this phi del s del phi is the number operator. So whenever you are changing scale, every time we have to change wave function renormalization of phi. So this is but it's a general generalized number of operator, because we are going to a lower energy scale lambda. It is no more phi del s del phi. These have this kind of terms too. And this part is given by the classical dimension. So here all variables are made dimensionless, and if you set del s del t 0, it gets fixed point action. And k pi p here is given by low energy propagator phi l. So usually for ease of calculation, we choose kp is equal to e to the power minus p square. Okay, so that is introduction of Polchinski equation. Now diagrammatically how it happens. So I have told that suppose I have to find the effective action. What will happen in 5, 6, 5, 8 all terms will come. So suppose 5, 6 term has come. So this 5, 6 term, and I want to put it in this structure, this part. So if I put in this part del s del phi, it gives two kind of diagram. Like everything, whatever you write, you can see in terms of Feynman diagram. That is better. That will give solution. So this part can get contracted in these two following ways. One is this diagram, another is this diagram. So all this here, all the propagators are high energy propagators. So that is the difference with the like continuum theory. So and high energy propagators are getting integrated. Yeah. So and this part will give from the first part of this this part. And if you put 1, 2, so these are all 4-point functions, and you can see. And if you find that how 4-point function will come from this part, so this always give a disjoint diagram I told. So this that part will give something from contact diagram and contribution on correction to the 2-point function. So if in the momentum external momentum, if you make 0, comes out the beta function of the theory. So you on both sides of the equation of this equation, and you will, that's how you will find the anomalous dimension or beta function in this way. Okay. Yeah, so that's how that is my end of introduction of ERG. Now what I'll do is I'll do the simplest case of derivation of ADS free scalar action from boundary CHEP-th using ERG. So this is basically a 3-step procedure in d-dimensional boundary theory, and write evolution operator of that ERG equation as a functional integral over a d plus d dimensional field theory, and then to map that D plus one dimensional field theory obtained in step 2 to an action of ADS space. Okay, so this 3 step is all over in the talk we will follow. Yeah. So first we write Polzinski equation in simple form. We are defining psi is equal to e to the power si, and suppose we are perturbing the Gaussian action. So where perturbing what the Gaussian action. Now if we perturb in such a equation takes this form, this form, then what we can do, we can find the evolution operator of this Polzinski equation, and following usual path integral formalism, we can write how the psi at some finite scale TF and some boundary value, final boundary value of phi f can be written in terms of initial configuration. These configurations are getting integrated. So this one is whatever is can be tell whatever is equivalent of I was telling in Faulkner paper in del SB del epsilon. They were telling this gives the radial Hamiltonian of the bulk theory. So this is a equivalent. It can be equivalent statement, but from the boundary where high energy can be written in terms of this evolution operator. So this action here can be interpreted as a D plus one dimensional theory, but it does not look like ADS action as of now because these have non-standard kinetic term. So what we will do in the third step is we will deal with the field redefinitions and change of variables so that it looks like ADS action.
I mean, in the evolution operator, can I ask you questions? In the evolution operator,
yes.
Usually the time ordering. There's a time ordering exponential of minus Ti to Tf. So why don't I see a time ordering here?
So time ordering means this is time ordering can have some boundary terms maybe like.
So I have a question which is
no
even simpler than Onindo's question. Isn't there a I in the evolution in the exponential of your evolution operator?
These are all Euclidean space.
These are Euclidean. So then maybe this is the clue. This is the clue to answering Aninda's question about this thing. So can you now answer his question? I don't think it has to do with the any boundary terms. If it is Euclidean, then you can say.
If it is in Hamiltonian, there is no boundary term usually. No? Like.
Yeah. Oh, yeah. Okay. So maybe
like
we can
come. That's why people work in Hamiltonian.
Oh, yeah. Maybe we can come back to this in the end. You can continue.
Okay. Okay. So yeah. So step 3 is as I. We are defining a new field Yp which is related to phi in terms of f. Where f we have defined in this way, where g was the Green's function of that theory, but we have put this kind of factor in view of lateral convenience that it can give some metric determinant term in this part of redefinition. Then if you change the variable, then z is equal to e to the power t. Okay, now choose f to satisfy. So this constant is important. You choose f to satisfy this constant. Then we get a free scalar ADS action. So that's how we get a free scalar ADS action here. the character, okay, some points here are yp and 1 by f satisfy the same equation. So this is important using this.
Sorry, what was f? I missed that point. F.
1 by f.
It
is somehow related to the g dot.
Can I see the previous page?
This function of the, yeah, this one is
right,
f is related to g.
Field division. F is related to G. Okay. Okay. Yeah.
Are there dots with respect to the or derivatives with respect to Euclidean time?
T here is the scale. T is
the scale.
Yeah, actually, this is T is not.
Yeah,
time.
like
I mean, in
ERG scale.
T is the RG scale. Oh, so then your first equation is quite sophisticated. Even the first equation is, requires a little bit more explanation, I think. So you're evolving from an initial scale Ti to a final scale Tf. Is that right?
Yeah. Yes.
This Polchinski's RG equation. Yeah, this d psi by dt is this.
Yeah, this is just each of this equation.
Integral of
okay. Okay, so it's like a diffusion equation. I mean,
yeah, diffusion equation.
It is like a diffusion equation, and then you're integrating over all p, and the g dot in Polchinski's equation is the derivative with respect to t, which is your scale.
With respect to t, yeah, scale.
Okay. And the h that you wrote in this equation, is that also coming from Polchinski's equation?
Yeah.
H dot.
In your step 2, you wrote an exponential of h.
Yeah.
So yeah.
That h is also coming from the Polchinski's equation, is it?
Yeah. This is the state operator of this diffusion equation.
Okay.
Actually, the time ordering now is I mean, this g dot, this is d by dt. I mean, if you exponentiate this equation, that g dot disappears. I mean,
and that's why it is G2 minus GF minus GI.
There's no time dependence in the next one. I mean, our scale dependence in the d squared. You have assumed that, is it? There's no scale dependence in d squared psi by d phi dot.
Yeah. So
there
maybe
is,
this maybe this is a question you can tell us in the end. You can tell us why G does not depend on the scale T.
G
depend on scale T. Actually, all of this is in dimensionless variable. So this P is a T by lambda. It's like that.
Yeah, but it's a total derivative. I mean, okay.
If G depends on scale T, then the tau ordering or T ordering will matter, right? When you integrate this equation.
That's a derivative. I mean, it's like a d by dg. So I think d by dt, and then I think she's
d by dt. Okay.
Yeah. So the psi doesn't depend on scale somehow. That's why that factors out, and then she has integrated tf minus t.
Okay, maybe we can discuss this in detail you can explain this in the end, no? We can come back to this point.
Okay.
Oh, but now there is time dependence. Okay.
Yes, what?
No, I thought that psi doesn't depend on scale, but later on you had an equation in which psi also depended on scale.
Yeah, everything depends on, like we are finding scale dependence of psi, right?
Yeah. Yeah, it's just that I'm wondering how
like
we
see here whenever we are doing when we are doing here, so effectively in this side we are differentiating with respect to phi. So we are not doing explicit any. So this whenever we are writing Polchinski equation. So first of this, whenever you are telling it scale dependence, it gives one times its classical dimension.
Okay.
Is that what you are asking?
No, it's just that how you're solving that exponential. So you have actually, in the second step, you have actually solved that rate equation. d psi by dt is equal to g dot, the second derivative. You have solved it. Just all the assumptions involved in solving that. The next step. After this is a rate equation, I mean, or diffusion-like equation for psi. And then you have actually integrated it in this step. So how have you actually, I mean, what are all the steps involved in getting from the last line of the previous transparency to step 2? That
I think first we this thing first we do NLP continuation. Okay, maybe I can talk about it later. Yeah.
Okay.
Okay, so yeah, so it is so here several points on field definition, change of variables, and choose f to satisfy a special constant, so that it now we get free scalar ADS action. Where several points to notice, yp and 1 by a satisfy same equation. So from this we can get some constant on f, and form of f is given by this linear superposition of Bessel functions. Okay, where mu is related with m square by m square plus I. So what? How to determine the m square is we knew that this 1 by a is related to g dot of the theory. So whenever we are considering a boundary theory, we know that what should be the g of that theory in the low energy limit. So in that limit, pz tends to 0. One can determine because that is given in the hand. We are starting from that theory, and one can find the n square. So and that n square what ATS CFT correspondence and that is yeah, and it forms basis of the vector and tensor calculus. Because in this paper, Kapath and it has been shown that from the scalar equation only, scalar field theory equation only, by some another field redefinition equations. Okay, so now we will. Yeah. If anyone have any question after this, maybe.
Yeah, I mean, just maybe you can just tell us the steps. I mean, so you got that solution for that diffusion, like the Polchinski's equation, and after that, you did some redefinition to one of the variables. Is that? I mean, just the steps. I mean, yeah, you did a redefinition.
Yeah. So here, this is the Euclidean action. Then we did this redefinition, and then this change of variable and f. This is the 3 step.
It's the change variables to f, and then there is a y. Y
is the bulk. We will
interpret it as a y.
We will interpret as bulk theory.
Bulk theory, yeah. So that equation seems to be that of the minimally coupled scalar y, the equation for y. The action for y is
I have a question about this step 3 that you wrote, which is that you chose f to satisfy a second order equation in z, right? So let me ask you this question slightly differently. How did you, what is the motivation for choosing this equation that F must satisfy? How did you get this equation that F must satisfy?
I think, okay, so one thing is if we put this, we get scalar equation, but that is like, another thing is like, if you choose this constant, then so these are all theories with the finite cutoff. So whenever we are changing, whenever you are changing delta phi, so that will give a different form than whatever continuum limit theory gives. So if you choose in this way, that all term of conformal invariance, conformal transformation. That is the motivation for choosing this. And also
This
one
equation
point
for
you
F.
can see that YP and yes.
No, if you're choosing that the equation obeyed by F is second order in Z. It's a second order differential equation in the variable Z, right? So my question was, I mean, why did you choose this? Why did you choose F to obey a second order equation? Why not first order? Why not some other order or even some other differential equation?
See,
Do you
here
understand my question?
in it, see this phi dot phi is there, right? Like if you want to bring something like so if you put Z is equal did this use this variable. Oh, okay.
Yes.
I agree. You see that this is phi dot phi, right? So this is whenever we are doing definitions.
Yeah. Actually,
So
I don't know whether it is just me, but I can't
yeah,
see your
this
cursor many
term.
times.
Yeah, sometimes it disappears and then it comes back.
So when you say phi dot,
Is my voice cutting off?
Yes, yeah.
for me also it cuts off. It's intermittent, yeah. But okay. So what were you saying about the phi dot squared term?
Yeah. So there is phi dot and phi dot in this in
the first line.
So whenever you are changing the variable, yeah. So whenever changing the scale z e to the power t, so this first term gives kinetic energy. Okay, and other terms are so yeah other so from there only you will get a second order. This part is actually coming from this redefinition. So just to make it contact with first scalar equation, we are making this transformation. Sorry, constant.
So it looks like you know the answer, Amindra, sort of.
Yeah.
Oh, is it that you get a second order differential equation because you have two phi dots in your first line?
Yeah, 2 5. Yeah.
Phi dot times. So if your action was something else, phi dot, there were 4 phi dots, then you would get a different equation. Is that right?
Yeah.
Okay, fine. So because you have to, and then I'm also guessing that you're throwing away a surface term in order that you write this in this form.
Yeah. Actually, we are throwing some
You
surface
have
term
thrown away a surface term. Okay.
and that has to be analytic actually.
So you have thrown away a surface term. The surface term is, where is your bound? Is 0 and infinity are your boundaries of Z, right?
Yeah.
Okay. I think I understand this slightly more, but
Yeah.
maybe I will ask you again after you finish.
This, I mean, m squared, right? In ADS CFT is connected to the dimension, right? Here it is just arbitrary. Is it? M squared is connected to the dimension of the operator in the boundary. Meaning
Yeah,
dimension
actually that's what. Sorry.
So
That's what I told in this slide.
is it going to come out, or is
Like,
it?
yeah, it is come out. You solve the equation, which constant you are getting. So 1 by f is in this form. This now nu is this is by this relation. Now what you know is you are starting from boundary theory. As 1 by f was related to g dot, so you know what will be your what should be your form of 1 by f. Fix the nu, and then you can find the m square. Should match with whatever this ADS-CHEP-th correspondence predicts.
Okay.
Is it okay?
So I mean, yeah.
Okay.
Hello.
Voice clear. Then I'll switch to the desktop maybe.
Yeah, it's breaking all the time actually, for me at least.
Hi. Okay, let's.
Yeah, for me also it is very intermittent. I don't know. Other people also should say whether it is clear for them.
Well, yeah. For me as well, it is intermittent.
Yeah, so I think there is there might be an issue with your device.
No, it's problem. Okay, I am trying to join from this thing. One minute. Let me disconnect and join from my thing. Okay, I think. Hi. I saw you. Hi, maybe I need sharing purpose in this desktop. Is my voice clear now?
Yes. I mean, this brief time it is clear. You're in what?
Okay, I have joined from desktop, but if it is not better, maybe I'll go back to iPad.
No, I mean, it's okay.
But here I am unable to share actually. Close share tray, it is like this.
Share. I don't know the permission. Pratik, is there some? Does
I
she
think
have?
you are still sharing from your iPad, so you have to stop
Oh,
sharing
soft
from
share.
your iPad.
Okay.
There's only one login. There is two. iPad one and.
No, I am not able to share actually. Okay, maybe I'll tell from my iPad itself.
I think she's muted.
Okay, hi. Is my voice clear now?
Okay, yeah, we'll see.
Okay, let's see. Okay. Okay, so answer is okay, right?
Okay. Yeah, you can go ahead. I mean, actually.
Okay. Okay, so now once we have ADS action, then correlator also can be calculated in standard way. Yeah, okay, sorry, I was in. Yeah, and also this is a simplest case. This forms basis of vector and tensor calculation. So we will now derive how the gauge motion in ADS is derived. So the key points and result is a boundary conserved current is expected to get mapped to gauge field in bulk. Now to do is action. What to do is first we have to find the action for boundary current using concept of auxiliary variable, and then ERG equation for that Wilson action for the auxiliary field. So mapping to ADS procedure is same. Currents in the case of ON symmetry, currents of ON symmetry, and another extra field redefinition because of presence of spacetime index. So specifically we will derive this equation of motion which is given in the paper of CHEP-th in 2012. So this is a scalar field equation with mass m square 1 minus d, and if in this where these phi's are all scalar fields, and if you redefine it in terms of Z A mu, one recovers source free Maxwell's equation. Okay. Now how to find Wilson action for composite operator. So first I will tell how not to deal with a composite operator. So usually what happens is, suppose J mu is the current and we want to find a composite operator by attaching a source to this current. Now as we flow to the low energy, usual concept of composite operator of ERG is given by linearized perturbation, which I have told mathematically here. Suppose OB is a bare operator in the theory, and we have sorry, this actually minus SBI should be in the exponential. So we are starting with a bare operator with the whole action, and we are integrating out the phi h part. So whatever we left is O lambda e to the power minus S lambda I. You can see this this thing in terms of like we are perturbing the bare action in terms of epsilon is small in terms of bare operator OP, and then how the S lambda at low energy lambda is changing, and the change which is proportional to epsilon, that change we collect and that we tell composite operator. Now as this definition, from this definition one can tell that this relation can be found. Like if you find correlator with O lambda and all the fundamental fields are with respect to S lambda, it is same as bare correlator. But as this is using linearized perturbation, if you put another field here and then rest of it fundamental field, that is not equal to whatever is bare correlator. So we would like to get back, but yeah, so that's why it is not useful. We want to find any kind, we want to find define a variable such that it can give back bare correlator at any part of the RG flow, any point of the RG flow. So that's why we will not use this definition of composite operator. Instead, we will use auxiliary variable. So auxiliary variable, suppose sigma mu is the auxiliary variable for the current. It is a dynamical field. That means it will be integrated out, but there is no kinetic energy at tree level. So it is just writing the Z mu in terms of, it's just a matter of inserting a delta function. So that is like the delta function is sigma mu is the current, and I have written the delta function in this basis. Okay, and when we do that, then we can also define J mu in this way, where e to the power s sigma mu is the thing which we want. This is a Wilson action in sigma mu. This is useful in the sense the form of e to the power s sigma mu is given by this form, and this can directly gives the value of any number of endpoint correlator in the bare. Another procedure is this phi del mu phi b. It is not all correct definition of current. It is correct definition if you are at bare theory. Whenever you are flowing to lower energy scale, it will take different corrections. So we have to define the sigma mu in such a way, and also whenever you are going to low energy version, the extra term, because of that it will not satisfy the current conservation law. So that's why we have to fix sigma mu in such a way that it is always satisfy current conservation law. So for that, what we do is first we gauge an external field A mu. We define an external gauge field A mu to gauge ON symmetry, like define a covariant derivative in this way where it is anti-symmetry, and define current in this with this definition. If we use this definition from gauge invariance of Z A mu, one can always ensure that sigma mu satisfy conservation law. Okay. So we take definition of Z mu as this way. So we are considering this operator, but Z here is defined by this. So if this both procedure one can combine, then that is the procedure for getting Wilson action for effective current, where you can see this new variable sigma mu as and a mu as kind of standard and alternate quantization in ADA-CFT, because one is a mu is the source, another is sigma mu. Here a mu was the source and sigma mu is like the operator itself. So it is like choosing between standard and or alternate quantization. But S sigma mu is useful in that sense. It always gives back this old correlator. Okay, so after this, actually things are straightforward. If anyone have any question, maybe I can take.
I mean, this A mu is just introduced as a gauge, right? I mean, you don't have kinetic term for A mu. I mean, you just have. I mean, do you have a kinetic term for A mu?
Oh, when there is d mu, there will be A mu. No, there is no kinetic term for A mu.
Yeah. So how does it come kinetic term in the bulk? I mean, you're claiming that you will derive an equation in the, which is basically the equation of the photon in the bulk, right? So that means it has all kinetic term, no?
Yeah, I will show that in.
How did you define the covariant derivative actually in your equation SB? Oh, there it is. And what is this? Is a multi-component scalar field, is it?
Yeah, it is ON symmetry. So
ON. So your gauge field A is the ON or SON gauge field. Is that right?
Yeah, ON gauge field. Yeah.
ON gauge field. Okay. Okay. Maybe I'll have some question later. Thanks.
Okay. Okay, if not there is any question. So now we'll derive the Polchinski equation for ON model for this variable sigma. One is like we always this sigma mu we have chosen in such a way that it always satisfy conservation law, and Z mu is gauge invariant, and chi mu is a variable our choice. So all the three variables we can choose as transverse. So we will all the variables after this is actually is transverse, and also we want to map sigma mu to gauge field in the level of kinetic term. So hence even if we put a mu is equal to 0, that will give kinetic energy. For other leading order, other subleading order term, we need AB. So if we do that, first to note that S lambda phi L sigma mu, this satisfy Polchinski equation of this form. Okay, where S lambda phi L sigma mu is like an external field, and phi h has been integrated up to scale lambda. And in this equation, what we do is, after evaluating everything, we can put lambda phi L is equal to 0, because phi L we want kinetic term in sigma mu or a mu. We don't want what is their interaction with phi L, so we'll put phi L 0 for simplicity. So if I do that, so if we do that, then we get a Erg equation of this. That is, leading order is of this form, where leading order is given by this term. So yeah, so actually what will happen is, whenever we are finding e to the power s lambda, so there is always a chi mu which comes with the delta function of the delta function, which defines sigma mu is equal to the current definition of current. So what we will do is, we collect quadratic term in chi mu, and when we collect quadratic term of chi mu, we replace in the first order, we can replace chi mu as delta of delta sigma mu, because we defined this S sigma mu is defined in this way. So we can replace chi mu in as delta of delta sigma mu. If we do that, then at first order term we get Erg equation like this, where this exact form of I is not important in order to get this kinetic energy term. It will come handy in whenever you try to calculate correlators. And as these sigma mu's are all transverse, so this only structure of I mu is possible is of this form. And leading order of this equation is given by this S lambda. So what we will do is, this is our Erg equation. Again, like before, we will find what is the evolution operator of this equation. So this evolution operator is given by this, and this is our Euclidean action of radial Hamiltonian. Okay, whereas yeah, so this action we want to transform it in such a way that it will go to the gauge ocean field. So these are the action I have written. This is the starting point. And then if we actually do the same three-stage procedure, which is in scalar case, we get this equation. You can easily see this looks like scalar only, but now number of scalar is d. So these are d number of scalar fields. So you can use the same field redefinition and change of variable, and you will end up with this scalar equation. But we have to fix the m square. So m square, so m square is like written same way that we know we have started with a boundary current. So we know what is the Green's function of the boundary current. From that we can fix what will be the form of f in the low energy limit, and from that we can find the m square, and it is coming to be 1 by d. And if you find the equation of motion from this scalar field, you'll get whatever CHEP-th in their 2012 paper they have derived. It is the same thing. And in this phi, if you redefine as z of phi mu, you will get source free Maxwell's equation. So that's how Maxwell's equation is derived.
I mean, is this in a gauge? I mean, this equation, is it in a gauge, definite gauge?
Yeah, there is gauge like you are using in bounded. Okay.
No.
Bounded.
This equation of motion in a definite gauge, or is it in? Is this the general?
Yeah, Z0. Sorry, this is like yeah, gauge is like you are putting AZ as 0. Like if you A is your Maxwell field, then AZ as 0.
The radial component of that is
Yeah.
0. But then how do you show that this theory has gauge invariance?
No, we are using gauge fixed version.
But I mean,
so
if you have to claim that it is a gauge field in the bulk, you need to show that it has that gauge invariance, right?
So we started with ZA mu, that was gauge invariant, right?
No, in the bulk. I mean, in the bulk, it should have a symmetry like A mu going to A mu plus D mu lambda. Here it is some gauge fixed version, so you had some D minus 1 scalars or whatever, some bunch of scalars. That's all. So right now it is just a bunch of scalars.
Yeah. So, but after this, there is a field redefinition, and we derived the Maxwell equation. Since I didn't write it here, but this is like you are defining mu as Z phi mu.
Okay.
So then you get back source free Maxwell's equation.
But in a gauge, I mean, in the sense that you have to show that it has to have gauge invariance, but that you're not. I mean, or have you shown it?
Actually, if it's Maxwell's equations, then they are gauge invariant anyway, right? Because
no, I think in a gauge, this is an equation in a particular gauge, is it?
Yeah, but if you write Maxwell's equations, they are just in terms of E and B. What I mean is, if it is a U1 gauge field, then the Maxwell's equation
is the vector potential. I mean, she's written it in vector potential. Phi nu.
Phi nu.
Yeah, phi nu is identified to be some vector potential, right?
I thought here this
phi mu is related to A mu, like a gauge portion.
Yeah.
Oh, so.
Yeah, so that's why I was wondering whether it's in a gauge or not. I mean, and then
this I mean, this equation, that your last equation, is that your Maxwell's equation?
Yes, if you put Z phi mu, you will get back Maxwell's equation in ADFC.
Z. But
so why is there just one gauge field? I mean, why is this a U1 theory? Hello?
Yes.
Why is this this abelian gauge theory? How is it that it became?
Abelian is because, see, it is not actually if you consider with free theory, it is abelian because we are starting, there is no interaction. So there is if you define phi 1 del mu phi 2, there is no interaction between phi 1 and phi 2. But if you put interaction, then it is non-abelian. At this point, it is like if you want to derive only kinetic energy, this is abelian. Like we don't need other properties.
Okay. Maybe I can ask you in the end.
Yeah. Okay, actually, this more or less ends my talk. So one thing is one can derive in the same way how bulk graviton. So there we have to map conserved EM tensor to gauge fixed bulk graviton action. So in boundary, conservation and tracelessness of EM tensor we are using, and in bulk we are using a ZM0 gauge, diffeomorphism invariance, and tracelessness of graviton. So one can define auxiliary variable sigma mu nu and map the radial action to equation of scalar fields. So number of scalar fields will be d into d minus 1 by 2 minus 1, and each will have mass 0. So that is a same procedure that whatever I have shown. So that ends my talk, and future direction is immediate direction is one had to put interaction in case of graviton and gauge field, and equivalent work have been okay. So an equivalent work have been done for scalar composite operator phi square for phi 4 theory in ON model. So in next order, in the if you put interaction, first order will be as same as Polchinski's form, but in the next order there will be some potential kind of term will come, and there also you can do field redefinition, and you can find bulk dual of whatever like theory you are considering in the boundary. And if you find bulk dual, maybe one can try to make connections of the above results with Vasilev's theory. And it will be also interesting to see. So at this point, whatever we have just found equation of motion or action of the bulk theory, but we don't know how bulk locality will arise in this scheme. So that is work for future. And also maybe one can try to extend this scheme in DSCFT because Poincare like patch is there also. There exists there also. And another problem maybe one can try is we are using is ERG, but what if one use dimensional regularization in boundary RG? So how one can interpret holographic RG in terms of dimensional regularization in boundary? So that ends my talk, and thank you. Question and comments.
Yeah, Shamanti, the long time back, Sangsik Lee tried to do what seems to me to be related to what you're doing here.
Yeah.
Comment on that?
Yeah. Actually, he also found bulk dual of one. But what is the exact relation? Hello?
Yes, sorry.
Can you hear me?
I got cut. You got cut, yeah.
Okay. So he also have found a bulk dual of ON model. Yeah, but what is the exact relation with our result? That I haven't checked thoroughly, but yes.
I'm coming back. I mean, those those fields you got some phi mu, right? They were just some n minus 1 set of scalars or something, right?
Yeah, d minus 1.
But they are supposed to be I mean, there's supposed to be some, vector potential. Therefore, they should have a gauge invariance, like, phi mu going to phi mu plus d mu chi or something. How do you show that symmetry? Because, I mean, it's supposed to be the Maxwell's action, no? You want to claim that it's a Maxwell's action in the bulk. But this equations of motion doesn't have that symmetry. It is arising as a gauge fixed version of it, right? I mean, by just looking at this equations of motion, how does
we can map to Maxwell's equation?
No, from Maxwell's equation, if you fix gauge, you get this. But you got only this, right?
But if you do the opposite one, you will get Maxwell. Like
opposite one.
Like the map is this one. So instead of this what Kabat have did, and if you do this, you recovers Maxwell equation.
But I mean, how do you show it has invariance? I mean, you'll just get one equation for some a nu, right? I mean, you'll get, and that will also come in gauge fixed version. Is it? Does it come in the gauge fixed version?
Yeah, gauge fixed version.
Yeah. So how does one show that it has gauge symmetry?
So maybe you can show that. Okay, maybe there are just two physical degrees of freedom, no?
That is only gauge fixed means
how
we have
used. No, but how do you show that that there are only two physical degrees of freedom? And because if it has only two physical degrees of freedom and it is it has sort of looks like a massless equation, then you can argue that it is a. Then you can argue that it's a. The underlying theory is a gauge theory, but can you show? Can you did CHEP-th and collaborators show that it has just 2 physical degrees of freedom?
Like if you want to show there is 2 physical, so in so this matching of boundary and
So
1
another way,
degrees of freedom.
another way of asking this question is, how do we know that this is not a equation for this is not an equation for a massive gauge field in some complicated disguise? Right, because if it were a massive gauge field, then of course then there is no gauge symmetry. So the question of gauge symmetry doesn't matter. There's no it does so gauge invariance doesn't matter. So the question I guess the question is how can we see that the equation that CHEP-th et al. Got, how can we see that it is not the equation for a massive gauge field, just written in some strange coordinates. You understand my question?
Okay. Yeah.
Okay. Okay, Symanthy, if there's no questions, then
Yeah, I don't have any other questions, but I just want to say that I have to leave. I have to take my daughter somewhere in 10 minutes, so that's sort of my cutoff.
yeah, I mean, I can just quickly have a discussion with Symanthy and then I can stop, I think.